Our view of the cosmos is fundamentally incomplete. We peer out into space, but our telescopes can only show us so much, limited by the vast gulfs of time and distance. This video explores a revolutionary tool that has changed everything: cosmological simulations. By the end, you will understand how these digital universes reveal hidden patterns that govern everything, from the birth of the first stars to the fate of galaxies. These simulations have uncovered cosmic structures and invisible forces we could never have seen directly, solving ancient puzzles and creating startling new ones. What do you think it means to truly know the universe? We are, in a very real sense, cosmic archaeologists. Our primary tool, the telescope, is a time machine. The light from the nearest star takes over 4 years to reach us. The light from the Andromeda Galaxy, our nearest large galactic neighbor, has been traveling for 2.5 million years. Every observation is a glimpse into the past, a single frame from a movie that has been playing for billions of years. We have countless frames, but they are all from different times, different distances, scrambled out of sequence. We see a newborn galaxy here, an ancient one there, but we cannot press play and watch one galaxy grow from infancy to maturity. It is like trying to understand the entire story of a forest by looking at a single photograph containing a seedling, a sapling, and a 1,000-year-old oak tree. You can guess the sequence, but you cannot witness the growth. This creates a profound limitation. The universe is not just what we see. Modern astronomy tells us that the stars and galaxies we observe, the glittering points of light, constitute less than 5% of the universe's total content. The rest is dark, invisible to our telescopes. Dark matter, which does not emit or absorb light, reveals itself only through its immense gravitational pull, bending the light from distant objects. Dark energy, an even more mysterious force, is causing the expansion of the universe to accelerate. These dark components dominate the cosmos, shaping its structure and destiny, yet they are completely hidden from direct view. Our telescopes show us the luminous actors on the stage, but they are blind to the stagehands, the directors, and the very machinery of the theater itself. Furthermore, the vast distances between objects are filled with clouds of gas and dust that can block or distort the light from more distant sources, like a cosmic fog. So what we see is not only ancient, it is also partial, obscured, and fundamentally static. We have a magnificent collection of snapshots, but we are missing the motion, the cause and effect, the hidden forces that write the story. To move beyond this gallery of still images, we needed a new kind of instrument, one that could run the movie of the universe forward from its beginning. The solution emerged not from a larger telescope, but from a different kind of laboratory entirely. This is the realm of the computational universe, a place where the laws of physics are written not in equations on a chalkboard, but in lines of code running on some of the most powerful supercomputers on Earth. It is the essential counterpart to observation, a way to test our understanding of cosmic history by literally building a universe from the ground up. Think of it as the ultimate controlled experiment. Astronomers cannot rewind time and watch our galaxy form, but they can create a digital twin of the cosmos and press play. This monumental task begins with 3 foundational ingredients. First, the rulebook, the established laws of physics. This includes Einstein's theory of general relativity, which describes gravity as the curvature of space and time itself, and the standard model of particle physics, which governs the behavior of all the known fundamental particles and forces. Second, the starting point. We need a snapshot of the infant universe, a seed from which everything grows. That seed comes from the cosmic microwave background, the faint afterglow of the Big Bang, which gives us a precise map of the universe when it was just 380,000 years old. It shows a cosmos that is almost perfectly smooth, but with tiny, whisper quantum ripples in density. Finally, we need the engine, raw computational power so vast it can calculate the gravitational dance of billions, even trillions, of particles of dark matter and gas over billions of virtual years. We feed these rules and this ancient map into the machine, and then we let physics take over. Gravity amplifies those tiny ripples. Dense regions attract more matter, growing into vast webs of dark matter filaments. Gas flows along these invisible highways, cooling and collapsing to spark the first stars. What unfolds is not a predetermined story, but a complex, emergent narrative where every single particle, every clump of gas can be tracked from beginning to end. We can watch a galaxy being born, see it collide with its neighbors, and observe how supernova explosions from its first stars blast material out into space, seeding future generations. In this digital cosmos, nothing is hidden. We can see the dark matter scaffolding directly. We can watch the push of dark energy as it stretches the virtual space between galaxies. We are no longer just archaeologists looking at scattered ruins. We are architects with a time-lapse camera, witnessing the entire construction from the first brick to the final, glittering city. This digital universe begins as a vast, empty cube of simulated space, a computational box with a very special property. Its edges are not walls but doorways. If a particle drifts out one side, it instantly reappears on the opposite side, as if the box were wrapped around on itself in every direction. This clever trick, called periodic boundaries, allows scientists to model a finite chunk of the cosmos without worrying about artificial edge effects, creating a window into an infinite universe. Within this box, we must represent everything from the invisible dark matter to the blazing stars. There are two primary ways to do this. The first treats space like a three-dimensional grid, dividing the void into billions of tiny cells. The physics equations for gravity, fluid motion, and radiation are then solved for each cell, calculating how energy and matter flow from one cube to the next. The second and more common approach for tracking dark matter is the particle method. Here, we do not simulate every single atom. That is impossible. Instead, we use what are called superparticles. Each one represents a colossal amount of material, perhaps the mass of a small galaxy. A modern simulation might follow the trajectories of not millions, but hundreds of billions of these particles. They are not physical objects, but mathematical points that carry properties like mass, position, and velocity. Their only rule is to obey gravity. Every single particle feels the gravitational tug from every other particle in the box. Calculating this directly for 1 trillion particles is beyond any computer, so scientists use ingenious shortcuts, grouping distant particles together to approximate their pull, allowing the calculation to focus on nearby, complex interactions. As the simulation runs forward from that smooth, ancient seed, gravity works its magic. Particles are drawn toward the subtle over-densities in the initial map. They begin to cluster, flowing along invisible rivers of attraction. Over billions of virtual years, a cosmic skeleton emerges, a vast, interconnected web of dark matter filaments. Where these filaments intersect, immense knots form, the future homes of galaxies. But this is only half the story. Gas must be added to the mix, and its physics is far more complex. Gas can be heated by starlight, cooled by radiation, compressed into stars, and blasted outward by supernova explosions. To model this, simulations use a hybrid approach, often tracking dark matter with particles, and the gas on a moving, adaptive grid that refines itself around areas of interest, like a forming galaxy. The scale of computation is almost beyond comprehension. A single run can take months on thousands of computer processors working in tandem, generating petabytes of data, a digital archive of an entire universe's history where we can rewind, pause, and zoom in on any event. We are not just watching a movie, we are conducting the ultimate experiment, asking what happens if we change one single law, one initial condition. What emerges from this colossal digital forge is a universe that looks, in its broad strokes, astonishingly like our own. The simulation revealed a structure of breathtaking elegance and scale. As those first dark matter simulations ran their course, scientists expected to see galaxies form, but they did not anticipate the grand architecture that would emerge from the chaos. What unfolded on their screens was not a random scattering of clusters, but a vast, intricate network, a cosmic web. Gravity, acting on those nearly imperceptible ripples from the early universe, did not simply pull matter into isolated blobs. It sculpted the universe into a sponge-like structure, with immense filaments of dark matter stretching across billions of light years, connecting dense nodes where thousands of galaxies would later gather. Between these threads lay equally immense voids, enormous bubbles of near emptiness spanning hundreds of millions of light years. This was the first great reveal from the digital cosmos, a pattern hidden in plain sight, written into the fabric of the universe by gravity itself. The most profound aspect of this discovery was its predictive power. These simulations produced the cosmic web years, even decades, before our telescopes were powerful enough to see it. Observational astronomy at the time saw galaxies, but mapping their positions in 3 dimensions across vast volumes of space was a monumental challenge. The simulations provided a bold prediction, a template for what the large-scale universe should look like. It was a map drawn from theory and computation, waiting for reality to catch up. And catch up it did. Massive galaxy surveys, like the Sloan Digital Sky Survey, began to meticulously chart the positions of millions of galaxies. When they finally compiled the data and constructed a 3-dimensional map, the result was a moment of stunning validation. There it was, etched across the observable universe, the very same web of filaments and voids the simulations had foretold. The luminous galaxies traced out the dense strands of the dark matter skeleton, like dew on a spider's web, revealing the hidden architecture. This confirmation was a watershed moment. It proved that simulations were not just elaborate video games, but powerful instruments of discovery. They could see patterns invisible to our direct observation, patterns dictated by the fundamental laws of physics. The cosmic web became the central organizing principle of modern cosmology, a framework that explains why galaxies are where they are, and why so much of the universe is a stunning, empty expanse. But the cosmic web was only the first layer of hidden architecture. Within the dense nodes of that web where galaxies gather, the simulations uncovered an even more intimate and invisible structure. Every single galaxy, from a small dwarf to a giant spiral like our own Milky Way, is not floating alone in space. It is embedded within a vast, spherical cloud of pure dark matter, a structure known as a dark matter halo. These halos are the true gravitational anchors of the cosmos. For decades, astronomers assumed these halos would be simple, smooth spheres, like a cloud of smoke around a lantern. But the simulations told a different, far more complex story. When scientists zoomed in on the formation of a single halo, they found a deeply nested architecture. At the very center, the density of dark matter spikes dramatically, forming what is called a cusp. This dense central knot is where the galaxy's visible stars reside, held in orbit by the halo's immense gravity. From that central cusp, the dark matter density falls off rapidly, but the halo itself extends outward for hundreds of thousands of light years, fading gradually into a vast, diffuse sphere that stretches far beyond the galaxy's last visible star. This entire structure, from the sharp central cusp to the incredibly faint outer edges, is completely invisible. We cannot photograph it, we cannot detect it with any telescope. Its existence and its detailed properties were first revealed entirely within the digital universe. The simulation showed that without this specific cuspy halo profile, galaxies as we know them simply could not form or hold together. The visible galaxy we see, with all its stars and gas, is just the luminous tip of a colossal, dark iceberg. Think of a city at night glittering with lights. From a distance, you see the city itself, but the simulations allowed us to see the entire island upon which that city is built, the hidden foundation that determines its shape, its size, and its very existence. This discovery transformed our understanding of galaxy formation. It is not that stars form first and then attract dark matter. The process is reversed. The dark matter halo forms first, carving out a deep gravitational well in the fabric of space. Ordinary matter, the gas that will become stars, then flows into this well. It cools, condenses, and begins to spark with light, painting the invisible scaffold with visible structure. So every spiral arm, every star cluster, every glowing nebula is tracing the contours of a darkness we can only map through simulation. But how do we know this simulated map is real? We test it against the universe we can see. The immense gravity of these dark halos bends the path of light from objects behind them, an effect called gravitational lensing. By studying how the images of distant galaxies are stretched and distorted, astronomers can literally weigh the invisible halo and measure its shape. The observations match the simulation's predictions with remarkable precision. We also see the halo's influence in the speed of stars orbiting at the far edges of galaxies. Those stars are moving too fast to be held by the gravity of the visible stars alone, implying a huge reservoir of unseen mass exactly where the simulations said the diffuse halo should be. Each of these observations is like feeling the shape of an object in a pitch-black room, confirming the detailed blueprint the simulations provided. The dark matter halo is no longer just a theoretical idea. It is a foundational component of the cosmos, a hidden skeleton whose form was first clearly seen not in the sky, but in the glow of a supercomputer's screen. Yet this powerful alignment between simulation and observation soon revealed a startling crack, a profound mystery that emerged directly from the code. When scientists zoomed their virtual telescopes onto a simulated galaxy like our own Milky Way, they saw not just a majestic spiral, but an entire entourage. The physics dictated that thousands of smaller dark matter halos should have survived from the early universe, swarming around the main galaxy like moons around a giant planet. These were the building blocks that never fully merged, the leftover fragments of cosmic construction. According to the rules, each of these small, dense halos should have pulled in gas and ignited stars, becoming visible dwarf galaxies orbiting their larger host. The simulation's prediction was clear and inescapable. A bustling satellite system of hundreds of faint, ancient galaxies should surround every large spiral. But when astronomers pointed their real telescopes at our own galactic neighborhood, the numbers did not match. They saw only a few dozen. Where the digital universe predicted a crowded sky of ancient satellites, our night sky showed a handful. This glaring mismatch became one of modern cosmology's most famous puzzles, known as the missing satellites problem. It was not a failure of the simulation, but rather its triumph, a case where it revealed a pattern in the data that simple observation had missed, a pattern that pointed directly to a gap in our understanding. The simulation said the dark matter halos must be there by the hundreds. Our eyes saw only empty space. So, which was correct? Was the simulation wrong about how dark matter clumps together? Or were we missing something fundamental about how galaxies, especially the smallest and faintest ones, actually form and survive? This tension between the predicted swarm and the observed silence became a powerful engine for discovery, forcing scientists to re-examine the messy, complex physics of star formation itself on the smallest cosmic scales. The answer lay not in the darkness but in the light. The early simulations that predicted the swarm of satellites had a crucial limitation. They focused almost entirely on the gravitational dance of dark matter, treating the luminous universe, the stars and gas, as a passive afterthought. But the cosmos is not so simple. To solve the mystery of the missing galaxies, scientists had to bring the light back into the picture. They had to simulate not just the invisible scaffold, but everything that happens upon it. This meant incorporating the staggeringly complex physics of ordinary matter, what cosmologists call baryonic physics. Baryons are the protons and neutrons that make up every star, every planet, and every one of us. They are the luminous 5% of the universe, and their behavior is wildly complicated. Unlike dark matter, which only feels gravity, baryonic matter feels all the forces. It can be heated, cooled, compressed, and blasted apart. It can glow with radiation and explode with catastrophic energy. To build a realistic universe, the simulations had to account for all of it: the birth of stars, the fury of supernova, the voracious appetite of supermassive black holes, and the subtle pressure of starlight itself. When scientists began adding these fiery processes into their digital universes, something remarkable happened. The puzzle of the missing satellites began to solve itself. The key was energy. In a small, fledgling dark matter halo, gravity is relatively weak. It can pull in a wispy cloud of primordial gas, cool it, and begin the delicate process of forming the first stars. But in these early simulations that included baryons, those first stars were not gentle. They were massive, brilliant, and short-lived. They died in spectacular supernova explosions within a few million years. And that is where everything changed. A supernova is not just a flash of light. It is a cosmic hurricane. The explosion unleashes an immense shockwave, heating the surrounding gas to millions of degrees and driving it outward at tremendous speeds. In a large galaxy with a deep gravitational well, this galactic wind might blow some gas out into the halo, but much of it will eventually rain back down. In a tiny halo with its feeble gravity, the effect is absolute. The supernova's wind acts like a cosmic blowtorch, violently heating and ejecting every last shred of star-forming gas from the small halo. With its fuel supply gone, star formation shuts down completely. The dark matter halo remains, a ghostly, invisible structure orbiting its host galaxy, but it is now dark in every sense of the word. It contains no stars, no glowing gas, nothing for our telescopes to see. It is a failed galaxy, a shadow of what might have been. By simulating this cycle of birth and explosive feedback, the digital universe revealed a hidden population. The satellites were not missing. They were all around us, but they were dark. They were the countless dark matter halos the pure gravity simulations had predicted, now rendered invisible by the very physics of starlight and explosion. This elegant solution did more than solve one puzzle. It showed that the visible universe we see is not a perfect map of the underlying dark matter. It is a filtered version, a census biased by violence. Only the halos massive enough to withstand the self-destructive fury of their first stars get to build the glittering cities we call galaxies. The rest remain in shadow, a silent majority revealed only by the predictive power of simulation. This galactic life cycle is a delicate balance between creation and destruction. We can watch it unfold in exquisite detail within the full physics simulations, where gas is not just a passive passenger but the active, turbulent fuel of cosmic evolution. It begins with a vast, diffuse cloud of hydrogen and helium, drawn into the deep gravitational well of a dark matter halo. As this gas settles, it begins to cool, radiating away its energy. As it cools, it condenses, collapsing under its own weight into denser and denser knots. Within these knots, the pressure and temperature become so extreme that nuclear fusion ignites and a star is born. This is not a solitary event. Across the forming galaxy, thousands, then millions of these stellar furnaces switch on, painting the dark scaffolding with light. But starlight is not the only product. The most massive of these new stars live fast and die young. Within only a few million years, they exhaust their nuclear fuel and collapse, triggering a cataclysmic supernova explosion. This is the crucial feedback mechanism. The supernova unleashes a torrent of energy, heating the surrounding gas to blistering temperatures and driving powerful shock waves through the galactic environment. This violent outflow does two things. First, it blows a vast bubble in the gas, sweeping it clear from the immediate neighborhood and temporarily halting further star formation in that region. Second, it enriches the gas with heavy elements forged in the star's core, elements like carbon, oxygen, and iron that are essential for building planets and, ultimately, life. This cycle, gas cools and collapses to form stars, stars explode and heat the gas, is the fundamental heartbeat of a galaxy. It is a self-regulating process. If star formation is too efficient, too many supernova erupt in quick succession, blowing out all the remaining gas and starving the galaxy of future fuel. If the feedback is too weak, the gas cools unimpeded, leading to a runaway burst of star formation that consumes all the gas in a relatively short, brilliant blaze. The simulations show that the most stable, long-lived galaxies are those where these forces achieve a rough equilibrium, where feedback carefully modulates the rate of creation. This elegant dance explains the great diversity of galaxies we see. A massive elliptical galaxy, often described as red and dead, is a system where this cycle has essentially concluded. Long ago, it likely experienced a ferocious burst of star formation, perhaps triggered by a major merger with another galaxy. The resulting feedback, possibly amplified by energy from a central supermassive black hole, was so powerful that it permanently expelled or heated nearly all the remaining gas. Without a cold gas supply, star formation grinds to a halt. The galaxy is left with an aging population of long-lived, cooler red stars, a quiet retirement after a tumultuous youth. In contrast, a spiral galaxy like our Milky Way is still in its star-forming prime. Its rotation helps organize the gas into a disk, and the feedback from supernova is strong enough to create bubbles and regulate the process, but not so strong as to completely quench it. Pockets of cold gas persist, allowing new stars to be born in its spiral arms even as older populations exist in its central bulge. The simulation lets us rewind and fast forward through these life stories, witnessing the specific events, the mergers, the bursts of activity that lead a galaxy down one evolutionary path or another. We see how the invisible hand of feedback, revealed only through these digital experiments, sculpts the observable universe, determining which galaxies blaze with newborn stars and which glow with the steady, fading embers of ancient light. But the most dramatic regulator in the galactic core was still missing from the picture. Even with supernova feedback, the simulations kept producing a universe that was too bright. The galaxies within them grew too massive, forming far too many stars, ending up as brilliant giants that simply did not match the observed population of galaxies in our real sky. Something was suppressing star formation on a colossal scale, especially in the most massive galaxies. The answer, it turned out, lay in the darkest hearts of galaxies themselves. To solve this scale problem, scientists had to introduce the most violent and energetic force in the cosmos into their digital universes, the fury of a feeding supermassive black hole. Nearly every large galaxy, including our own Milky Way, hosts one of these incomprehensibly dense objects at its center, with masses millions or even billions of times that of our Sun. For most of a galaxy's life, a supermassive black hole is quiet, a dormant monster. But when gas and stars are funneled toward it by galactic collisions or instabilities, the black hole awakens. As matter spirals inward at nearly the speed of light, it forms a searing, glowing disk of plasma, an engine of unimaginable power called an active galactic nucleus. The energy output can outshine the entire rest of the galaxy for millions of years. Early simulations treated these black holes as simple gravity sinks. But to make the digital universe look right, scientists had to model the energy they release back into their surroundings, a process called a GN feedback. This is not a gentle nudge. As the black hole feasts, it can launch jets of charged particles traveling at near light speed, shooting out for tens of thousands of light years. It also drives tremendous winds of hot gas blowing outward in all directions. This energy does not create stars, it obliterates the conditions needed to make them. The simulation shows this feedback acting like a cosmic thermostat. When a galaxy is very active, funneling huge amounts of gas toward its center, the black hole feeds aggressively. The resulting explosion of energy heats the surrounding galactic gas to such extreme temperatures that it cannot cool down and collapse to form new stars. It effectively shuts off or quenches star formation across the entire galaxy. This solves the mystery of the overlarge galaxies. Without this regulatory mechanism, gas would cool unimpeded, relentlessly forming stars until it was all used up. With it, the black hole's fury self limits the galaxy's growth. It is a stunning revelation from the simulation. These black holes, once thought of as mere destructive curiosities, are in fact master architects. They are the unexpected governors of galaxy growth, determining not just the size of their host galaxy, but the very timeline of its stellar life. A galaxy's fate, whether it blazes with youth or settles into a quiet, red maturity, is often dictated by the feeding habits of the darkest object at its center. The simulation allowed us to see this invisible relationship, this feedback loop between the largest and smallest scales, proving that to understand the light of the cosmos, we must first understand its deepest darkness. But the influence of the cosmic web runs even deeper, shaping galaxies in a way that feels almost personal. The simulations have revealed that a galaxy is not an island. Its very identity, the direction it spins, is written in the invisible currents of the larger universe. When scientists began analyzing the properties of thousands of virtual galaxies, they noticed a subtle but profound trend. The galaxies did not spin at random. Their rotation seemed to whisper a secret about the cosmic geography they called home. Picture a vast filament of the cosmic web, a river of dark matter and galaxies stretching across the emptiness. According to the simulations, the galaxies living within that filament exhibit a distinct preference. Their axes of rotation, the imaginary line around which they spin, tend to align themselves with the direction of the filament itself. It is as if each galaxy is a log caught in a powerful current, naturally turning to point along the flow. This alignment is not perfect, but the statistical signal is clear and strong. A spiral galaxy forming inside one of these immense threads will most likely spin so that its disk is oriented along the filament's length. This discovery was startling because it connects the very large to the very small in a direct physical way. The pattern emerges from the initial conditions of the universe, from those quantum ripples in the ancient afterglow. As gravity pulls matter into the filaments, it does not just collect it, it imparts a subtle torque, a gentle twist. The gas flowing into the forming galaxy inherits this preferred direction of rotation, setting the spin for billions of years to come. This is a pattern we could never have deduced by looking at real galaxies in isolation. From our vantage point, a single galaxy's orientation tells us nothing. It is only by constructing a universe and examining the relationship between thousands of galaxies and their environment that this hidden order becomes visible. The simulation acts as a cosmic sociologist, revealing how the neighborhood shapes the individual. It shows us that the majestic pinwheel of a spiral galaxy is not just a product of its local conditions. but a fossilized record of the vast, streaming currents of the cosmos in which it was born. Its spin is a memory, a lasting imprint of the universe's largest structures upon its most beautiful islands of light. The spin of a galaxy is a memory written in the flow of the cosmic web, but its story is written in collisions. We look at a magnificent spiral like Andromeda and see a single, coherent island of light. It appears whole and eternal, yet the simulations reveal this is an illusion, a snapshot of a being that is the product of a violent and ongoing biography. This is where the digital universe truly becomes a time machine for galactic history, a form of cosmic archaeology conducted not with a shovel, but with a rewind button. We can select Andromeda in the simulation, trace the paths of its stars backward through billions of virtual years, and watch its story play in reverse. What we see is not a serene growth, but a relentless series of mergers and acquisitions. That beautiful, unified disk was once dozens of smaller galaxies, independent islands of stars and dark matter, each orbiting in the early universe. Over time, drawn together by gravity, they began to dance. These dances were not gentle. They were catastrophic mergers, gravitational tangles that shredded smaller galaxies into stellar streams, warping disks and triggering bursts of frantic star formation. The simulation shows us the pattern, a foundational rhythm of the cosmos called hierarchical growth. The universe builds large structures from small ones. Tiny dark matter halos form first. They merge to build larger halos which attract more gas and merge again. A galaxy like Andromeda is not a pristine creation. It is a corporate empire built over billions of years by absorbing its competitors. The visible evidence of this violent past is still there, etched into the galaxy itself, but we need the simulation's guidance to know where and how to look. Astronomers, armed with the simulation's predictions, now scan real galaxies for the faint, ghostly signatures of these ancient mergers. They find them in the form of vast, diffuse shells of stars thrown out during collisions, or in faint rivers of stars called stellar streams, orbiting in the galactic halo, the torn-apart remnants of a dwarf galaxy slowly being digested. These are the archaeological artifacts of galactic history. Without the simulation, we might see these faint features as mere curiosities. With it, we understand they are chapters in a biography. They tell us which mergers happened, how long ago, and from what direction. They reveal that the serene galaxy we admire on a clear night is, in truth, a living museum of its own violent construction, a palimpsest where the stories of countless smaller galaxies are written over one another in the ink of starlight. This pattern of hierarchical growth, first revealed in the clean logic of the simulation, is now a cornerstone of our understanding. It explains the diversity of galaxy shapes, the distribution of old and new stars, and even the placement of supermassive black holes. Every large galaxy is a collective, a community of smaller galaxies that lost their individual identities to create something new. We are not looking at a finished portrait, but at the latest frame in a billion-year-long film of assembly. This violent assembly of galaxies took place in a universe cloaked in darkness. For hundreds of millions of years after the Big Bang, the cosmos was not a transparent sea of stars, but a dense, opaque fog. It was filled with neutral hydrogen gas that absorbed any light trying to pass through it. The universe was a featureless, murky void. The transformation from this primordial fog to the clear, star-filled expanse we see today is one of the most dramatic events in cosmic history, known as the Epoch of Reionization. It is a chapter we cannot read with our telescopes directly. The first stars and galaxies that caused this great change are so incredibly distant that their light has been stretched into the far infrared, reduced to a faint whisper by the expansion of the universe. They are hidden behind eons of time, their signals drowned out by the glow of our own galaxy. To witness this cosmic dawn, we must once again turn to the simulation to rebuild the moment the universe turned on the lights. We begin in the aftermath of the Big Bang with a cosmos cooling and expanding. Ordinary matter is a soup of protons, electrons, and light, all bouncing around in a hot, dense plasma. As it continues to cool, about 380,000 years later, electrons and protons finally combine to form stable, neutral hydrogen atoms. For the first time, the universe becomes transparent to light. This is the moment that gives us the cosmic microwave background, that ancient snapshot. But then, darkness returns. There are no stars yet, no sources of light. The universe enters what astronomers call the cosmic dark ages, a period lasting over 100 million years where the neutral hydrogen gas simply sits, waiting. Inside the simulation, we watch the first structures begin to stir. Tiny dark matter halos, the very first to form, begin to pull in wispy filaments of this primordial hydrogen. The gas cools, condenses, and in the hearts of these small, pristine halos, the very first stars ignite. They are not like the stars we know today. Born from gas that contains only hydrogen and helium with no heavier elements, these first stars, called population 3 stars, are thought to be monsters. They could be hundreds of times more massive than our Sun, blazing with a ferocious, ultraviolet intensity, and living only a few million years before dying in colossal supernova. It is the ultraviolet light from these first stars and the earliest galaxies that becomes the agent of cosmic change. The simulation models this radiation with exquisite care. Each of these first stars is a powerful ultraviolet lighthouse. The photons it emits do not travel far before they encounter a neutral hydrogen atom. When a high-energy ultraviolet photon strikes such an atom, it rips the electron away from the proton, ionizing it. The atom is torn apart, returning to a charged state of plasma. But the surrounding fog is so thick that the photon cannot travel very far before being absorbed. The result is not a wave of light sweeping across the universe, but the slow, gradual growth of bubbles. Around each cluster of early stars, a sphere of ionized, transparent plasma begins to form. Inside the bubble, the fog has cleared. Outside, the neutral hydrogen still blocks all light. We watch in the simulation as these bubbles of light begin to multiply. More stars form in neighboring halos, creating their own ionized spheres. The bubbles grow, their edges pressing outward into the neutral fog. Over millions of years, they begin to touch, then merge, creating ever larger regions of transparency. It is a cosmic percolation process, like watching air bubbles rise and connect in a pot of water just before it boils. The simulation maps this intricate process in 3 dimensions, showing how these transparent regions weave through the cosmic web, following the filaments of dark matter where the first galaxies are born. The entire universe is being remade not by a single event, but by the collective effort of countless early stars, their radiation eating away at the darkness. This era of reionization did not happen everywhere at once. It was a patchwork, a gradual process that took hundreds of millions of years to complete. The simulation allows us to fast forward through this pivotal transition, to see the moment when the final, isolated pockets of neutral hydrogen are finally evaporated by the relentless ultraviolet glow of young galaxies. By about 1 billion years after the Big Bang, the fog has lifted completely. The universe is now transparent, a state it has maintained for over 13 billion years, allowing the light from all subsequent generations of stars and galaxies to travel freely across the cosmos, all the way to our telescopes. Without the simulation, this epoch would be a profound mystery, a blank page between the afterglow of creation and the first galaxies we can faintly see. The digital universe fills in that page, showing us how the first sparks of starlight collectively performed the ultimate cosmic act of cleaning, burning away the primordial fog to unveil the universe we call home. The light from those first stars did more than clear the cosmic fog. It forged the very chemistry of life. Within the hearts of those massive, early stars, and in the violent furnaces of their deaths, the universe began a slow, patient alchemy. Hydrogen and helium, the only elements born from the Big Bang, were fused into heavier ones: carbon, oxygen, iron, and all the rest. This process, the creation of metals as astronomers call all elements heavier than helium, is the hidden chemical story of the cosmos. For decades, we could only guess at its timeline and its geography. But with simulations that now include the intricate physics of stellar evolution and supernova explosions, we can trace the spread of these elements like detectives following a trail of cosmic pollution. This revealed pattern is known as chemical enrichment, and it has become one of the most powerful tools for reading the history of our galaxy. The process begins with a single star. In the simulation, we can tag individual particles of gas, watching as they are drawn into a collapsing cloud. We see the virtual star ignite, its core becoming a nuclear fusion reactor. For millions of years, it steadily cooks hydrogen into helium. In the most massive stars, the fusion process continues, layering the core like an onion with progressively heavier elements, all the way up to iron. Then the star dies. The simulation models the catastrophic collapse and rebound, the supernova explosion that blasts the star's outer layers, now rich with these newly forged metals, out into the surrounding space at nearly the speed of light. This ejected material, a cloud of enriched gas, mixes with the pristine hydrogen and helium of the interstellar medium. It is a form of pollution, but it is the most vital pollution imaginable. That cloud, now seeded with carbon, oxygen, and iron, will eventually cool and collapse again under gravity. The next generation of stars that form from this material will therefore begin their lives with a small but crucial metallic heritage. They are born with the ingredients for rocky planets already present. The simulation lets us run this cycle forward on a galactic scale. We watch as waves of enrichment sweep through the forming galaxy. The first regions to form stars become the first to be enriched. These are typically the dense central bulge of a galaxy. The ejected metals from its earliest, most massive stars remain largely trapped by the strong gravity of the galactic core, leading to a rapid rise in metallicity there. In contrast, the outer reaches of the galactic disk form stars more slowly. Gas from the pristine outer halo takes longer to fall in, and supernova winds can more easily blow enriched material out of these regions with their weaker gravity. This creates a powerful gradient, a clear chemical pattern. The simulation predicts that stars in the inner galaxy should be, on average, much richer in heavy elements than stars in the outer galactic suburbs. This is not just a theoretical prediction, it is a fossil record we can excavate. Astronomers have measured the metallicities of hundreds of thousands of stars in our own Milky Way. The observed pattern is a perfect match. Stars in the galactic bulge are indeed metal-rich. As you move outward along the spiral arms, the average metallicity of the stars steadily declines. The galaxy's history is written in the chemical composition of its stars, and the simulation provided the key to deciphering it. We can even use this chemical fingerprint to identify cosmic immigrants. When the simulation shows a small dwarf galaxy being torn apart and absorbed by a larger one, it also tracks the chemical signature of the ingested stars. These stars, formed in a different environment with its own enrichment history, will have a distinct metallicity and ratio of elements compared to the native population. In our own galactic halo, astronomers have found streams and clusters of stars with oddly similar and often low metallicities. These are the predicted remnants of ancient galactic mergers, their shared chemistry a tag identifying them as a family, a surviving group from a galaxy that no longer exists. The simulation did not just predict where metals should be, It revealed how the chemical tapestry of a galaxy is woven from countless individual stellar lives and dramatic mergers. Every element in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe, was forged in the heart of a star that lived and died long before our sun was born. The simulations show us the grand pattern of that distribution, the billions-year journey that scattered those essential atoms across the galaxy and eventually into the cloud that would form our solar system. We are not just made of star stuff, as the saying goes. We are made of star stuff that followed a very specific, simulated path through cosmic history. These chemical patterns are a silent testament to cosmic history, but how do we verify the invisible architecture they hint at? The key lies in a phenomenon predicted by Einstein over a century ago, a celestial illusion that has become our most powerful tool for mapping the dark universe. This is gravitational lensing, a direct consequence of his theory of general relativity, which tells us that mass curves the very fabric of space and time. Imagine space as a vast, taut rubber sheet. Place a heavy weight on it like a bowling ball and the sheet dips. Now roll a marble past the bowling ball. The marble's path will bend as it travels through the curved sheet. Light behaves in exactly the same way. When the light from a fantastically distant galaxy travels across the cosmos, its path is not perfectly straight. If that light passes near a massive object, like a cluster of galaxies embedded in its immense dark matter halo, the space around that cluster is curved. The light follows that curvature, bending around the mass. From our perspective, the image of the distant galaxy is distorted. It might be stretched into a faint arc, or even appear as multiple, identical images around the foreground cluster, like a cosmic mirage. This is not a flaw in our telescopes. It is the universe itself acting as a lens, magnifying and warping the light from objects behind it. For decades, gravitational lensing was a theoretical curiosity, difficult to observe. But with the advent of incredibly sensitive digital sky surveys and the Hubble Space Telescope, it moved from theory to a standard observational technique. We now see these elegant arcs and multiple images throughout the universe. Yet to truly understand them, to use them as a map, we need a guide. That guide comes from the simulations. The digital universes we build provide the crucial link between theory and observation. Within a simulation, we have a perfect, complete map of the dark matter. We know the exact mass, shape, and position of every single dark matter halo, from the smallest clumps to the largest galaxy clusters. With this perfect knowledge, scientists can run a virtual experiment. They can place simulated distant galaxies behind these simulated dark matter structures, and using the laws of general relativity, calculate precisely how the light from those background galaxies should be bent and distorted. The simulation generates a predicted lensing pattern, a specific blueprint of arcs, rings, and image multiplicities that should appear on the sky if our model of dark matter is correct. This is the power of the digital cosmos. It takes an invisible component, dark matter, and tells us exactly what its gravitational signature should look like. Then we take our most powerful telescopes and look at the real universe. We find a massive galaxy cluster and study the distorted images of the galaxies behind it. We measure the shapes of thousands of those faint background galaxies, detecting the subtle, systematic stretching caused by the cluster's gravity. This process, called weak gravitational lensing, allows us to construct a mass map of the foreground cluster. We are essentially weighing the cluster by measuring how much it bends light. The moment of truth comes when we compare this real, observed mass map with the predicted map from the simulation. Do the arcs appear where the simulation said they should? Does the overall distortion of the background galaxy shapes match the predicted shape of the dark matter halo? The answer, time and again, is a resounding yes. The alignment is not perfect because the real universe is messier than our simulations, but the statistical agreement is astonishing. This is how we test our cosmological model with rigor. It is a continuous loop of prediction and verification. The simulation makes a bold forecast about an invisible structure. Observation, guided by that forecast, goes out and measures the structure's gravitational shadow. The match confirms that our digital universe is capturing something profoundly true about the real one. More than just a test, this process lets us map dark matter directly. By carefully analyzing the lensing distortions across huge swaths of the sky, astronomers can now construct three-dimensional maps of the cosmic web's dark matter skeleton, tracing the filaments and voids that the simulations first revealed. We are no longer inferring dark matter from the motion of stars. We are seeing its gravitational imprint on the fabric of space itself. Each distorted galaxy is a data point, a witness to the unseen mass that lies between it and us. Through this elegant interplay of digital prediction and celestial observation, we are finally bringing the dark universe into focus, proving that the patterns we first saw glowing on a supercomputer's screen are, in fact, written across the heavens. Gravitational lensing confirms the dark architecture, but the simulations have also revealed a second, equally profound puzzle. This one focuses not on the missing small galaxies, but on the ones that should have been the brightest and most obvious. It is called the too big to fail problem, and it strikes at the heart of our understanding of dark matter's nature. The logic is straightforward. Within the vast halo of a galaxy like our Milky Way, the dark matter subhalos come in a range of sizes. The pure gravity simulations predict that a handful of these subhalos should be exceptionally massive and dense. Their gravitational wells are so deep and strong that they should have easily captured and held onto vast amounts of gas early in the universe's history. According to all our models of galaxy formation, these particular subhalos are too big and too gravitationally powerful to have failed at forming stars. They should have ignited into brilliant, sprawling dwarf galaxies, the dominant jewels of our galactic satellite system. They should be, by far, the brightest objects orbiting the Milky Way. Yet when we look at our real galactic neighborhood, this predicted elite group of luminous satellites is simply not there. The dwarf galaxies we do see, like the large and small Magellanic Clouds, are significantly less massive and less luminous than what these prime subhalos should have produced. The most massive dark matter clumps around us appear to be dark, hosting only faint, sparse collections of stars or nothing at all. This presents a serious tension. The cold dark matter model, which works so beautifully on the largest scales to produce the cosmic web, seems to overpredict the amount of structure on this smaller, galactic scale. It creates subhalos that are too dense, too robust to align with the observed population of satellite galaxies. Solving this puzzle forces scientists to consider two broad possibilities. The first is that our understanding of galaxy formation within these halos is still incomplete. Perhaps there is a feedback mechanism even more effective than supernova at suppressing star formation in these specific, massive halos. Maybe the reionization of the universe was so intense and early that it stripped gas away from these particular clumps before they could get started, despite their strong gravity. The second, more radical possibility touches on the fundamental properties of dark matter itself. Could dark matter be slightly different than the simple, cold, and collisionless particle we have long assumed? Some theories propose dark matter that is slightly warm, meaning its particles had a small amount of intrinsic motion in the early universe. This warmth would smooth out the smallest density fluctuations, preventing the very densest, smallest scale clumps from forming. The result would be a halo populated with fewer of these extremely dense substructures, potentially bringing the simulations into better agreement with the observed, quieter satellite population. Other ideas involve dark matter that can interact with itself, through an unknown force, allowing it to scatter and smooth out the central cusps of halos. Each of these theoretical adjustments makes a distinct prediction that can be tested with ever more detailed simulations and by searching for faint stellar streams or other delicate signatures in our galaxy's halo. The too big to fail problem is not a failure of the simulation method, but another triumph of its predictive power. It has highlighted a specific, quantitative discrepancy that mere observation could only sense as a vague unease. By providing a precise forecast of what should be there, the digital universe has given us a clear target, a cosmic anomaly that demands an explanation. It reminds us that every tension between prediction and observation is not a roadblock, but a signpost pointing toward a deeper layer of truth waiting to be uncovered. Our universe is the only one we will ever know firsthand. We occupy a single, fixed point within a single, unfolding cosmic history. This is a profound and often overlooked limitation of being an observer. Every measurement we take, every galaxy cluster we map, every filament of the cosmic web we trace, is just one sample, one specific realization of how the laws of physics could have played out from the initial conditions of the Big Bang. The patterns we see around us, from the precise arrangement of nearby galaxies to the size of the largest void, might be typical of the universe as a whole, or they might be a local quirk, a statistical fluke of our particular neighborhood. This uncertainty is known as cosmic variance, and it is an inherent source of noise in our understanding. Think of it like this. If you wanted to understand the average height of humans, you would not measure just one person. You would sample many people from different places and backgrounds to get a true sense of the global average, but we cannot travel to another universe to take a second measurement. We are stuck with our one data point. This is where the power of the simulation shifts from being a time machine to becoming a cosmic laboratory of possibilities. Scientists do not just run one simulation of the universe, they run thousands. Each one starts with the exact same laws of physics and the same overall recipe, the same cosmological model. But they each receive a different, randomly generated seed for those initial quantum ripples. It is as if nature rolled the dice at the moment of creation, and we are living in the outcome of one particular roll. The simulation allows us to roll the dice again and again and again. By generating this vast ensemble of statistically identical but uniquely varied universes, we can finally measure cosmic variance. We can ask, in how many of these virtual universes does a structure like the Sloan Great Wall, an immense filament of galaxies hundreds of millions of light years long, appear? How often do we find a void as exceptionally empty as the one in the constellation Boötes? The simulations give us a distribution, a sense of what is common and what is rare. They allow us to place our single, observed universe within a crowd of its possible siblings. This process has led to some startling insights. Some features we once thought might be unusual, like the specific alignment of galaxy spins along filaments, turn out to be quite common across the ensemble. They are a robust prediction of the model. Other structures, however, give us pause. When scientists compare the largest observed clusters and voids to those in the simulated ensembles, a few appear to be at the extreme edge of the statistical distribution. They are not impossible within the standard model, but they are uncommon. This does not necessarily mean our model is wrong. It might simply mean we live in a slightly unusual part of the cosmos. A reminder that even in a universe governed by strict laws, chance still plays a role in the local scenery. More importantly, this ability to quantify cosmic variance tells us the limits of our own knowledge. It defines the precision with which we can ever hope to measure certain properties of the universe from our one vantage point. The simulations provide the error bars on our cosmic maps, a humble acknowledgement that while we can reconstruct the story of the cosmos, we may never know for certain if our chapter is entirely representative of the whole book. This statistical landscape sets the stage for our most daring observational quest. After billions of years of cosmic evolution, we are now peering back toward the very beginning, to the epoch when the first galaxies ignited. The James Webb Space Telescope, our most powerful time machine, is now sending back its first deep-field images, revealing a universe filled with faint, red smudges of light from an era only a few 100 million years after the Big Bang. But how do we know what we are looking at? How do we distinguish a truly primordial galaxy from a closer, dimmer one? The answer lies in a sophisticated partnership between the virtual and the real. Before Webb ever launched, scientists were already using their most advanced simulations to predict what it would see. They ran their digital universes forward from the cosmic dawn, not just tracking the formation of stars and galaxies, but simulating the very process of observation itself. They placed virtual telescopes inside their simulated cosmos and generated synthetic images, applying the exact resolution, sensitivity, and color filters of the James Webb's instruments. These mock universes became a crucial field guide, a catalogue of expected appearances. The simulations told researchers that the earliest galaxies would not look like the majestic spirals we see today. They would be small, chaotic, and blazing with the light of young, massive stars, their light stretched into the infrared by the expansion of the universe. They would appear as tiny, red blobs, but so would many other objects like dusty galaxies from a later era. To tell them apart, scientists used the simulations to understand the subtle signatures within that light. By analyzing the synthetic data, they learned that a galaxy's color across different infrared filters, its brightness and its shape can reveal its distance, its age, and even the rate at which it is forming stars. When a new deep-field image from Webb arrives, astronomers do not just look at it. They compare it pixel by pixel to thousands of these simulated images. They ask their digital universes, does this collection of faint red smudges match what we predicted for a universe 500 million years old, or 700 million? The process is like matching a fingerprint. The pattern of galaxies, their colors, their clustering, all leave a distinct imprint that can be compared to the simulation's forecast. This allows teams to interpret the raw data to confidently say, this particular smudge is one of the earliest galaxies ever seen, while that one is a slightly later arrival. But the comparison goes deeper than mere identification. It is a rigorous test of our entire story of cosmic dawn. When the first Webb data was compared to the best simulations, something fascinating happened. The early universe appeared to be more structured, with more bright, well-formed galaxies than many models had anticipated. This is not a failure, but a thrilling moment of discovery. The simulations provided a clear baseline, a prediction of what should be there if our standard model was complete. The discrepancy highlights where our understanding is incomplete, perhaps in how quickly stars formed in those first halos, or how efficiently their light escaped into the cosmos. Each mismatch is a clue guiding theorists to refine their code, to add new physics, and to run new simulations that inch closer to the reality Webb reveals. We are not just using simulations to explain what we see. We are using the deepest observations in history to stress test and improve our virtual universes. It is a continuous dialogue between prediction and reality, where each new faint smudge of light from the edge of time helps us rewrite the opening chapters of our cosmic story. The deepest observations from telescopes like Webb provide a powerful reality check, but they only give us one version of the story. To truly understand the recipe that built our cosmos, we must step into a laboratory of infinite possibilities. This is where simulations transform from reconstructing a single history into exploring a multiverse of potential universes, each governed by a subtly different set of rules. The fundamental constants of our universe feel fixed and absolute. The strength of gravity, the density of dark energy, the initial amplitude of those quantum ripples, these numbers seem written in stone. Yet for scientists, a profound question lingers. Why these numbers? Could they have been different? And if they were, what kind of cosmos would have emerged? We cannot rerun the real universe with new settings, but we can do the next best thing. We can build thousands of them inside a supercomputer. This process begins by identifying the key ingredients in our cosmological recipe. Think of them as the dials on a vast cosmic control panel. One dial controls the amount of dark energy, the mysterious force accelerating the universe's expansion. Another sets the overall density of dark matter. Others adjust the initial smoothness or lumpiness of the early universe, or the precise ratio of ordinary matter to dark matter. In a monumental computational experiment, researchers run vast ensembles of simulations. In each run, they turn these dials to new positions, creating a universe with a unique combination of parameters. Then they press play and let physics unfold for billions of virtual years. The result is not one cosmos, but a sprawling library of possible cosmoses, a digital multiverse where every book tells a different story of cosmic evolution. The goal is not to find the most interesting or beautiful universe, but to find ours. Scientists then analyze each simulated universe with the same tools astronomers use on the real night sky. They count the number of galaxies in massive clusters. They measure the statistical distribution of voids and filaments in the cosmic web. They calculate the rate at which galaxies collided and merged throughout cosmic history. They generate synthetic telescope images and mock galaxy surveys. Each universe leaves a distinct fingerprint, a pattern of large-scale structure that is a direct consequence of its specific parameter settings. The next step is the ultimate matching game. They compare the fingerprint of each simulated universe to the fingerprint of our own, as painstakingly measured by projects like the Sloan Digital Sky Survey and the Planck satellite. The pattern that emerges from this colossal comparison is both elegant and powerful. The vast majority of these alternate universes look nothing like home. Turn the dark energy dial too high, and the universe expands so rapidly that matter never clumps together into galaxies. You get a cold, dark, and empty cosmos. Turn it too low, and gravity wins too quickly, causing the entire universe to collapse back on itself in a premature reversal of the Big Bang. Adjust the initial lumpiness too high, and you get a universe overrun with enormous black holes and chaotic mergers far exceeding what we observe. Adjust it too low, and structure formation is so sluggish that only a few faint galaxies ever form. Amid this cosmic haystack, only a narrow range of parameter combinations produces a universe that matches the intricate patterns we see around us. A universe with galaxies, clusters, and a cosmic web that looks statistically like our own. This process places exquisitely precise constraints on the real values of those fundamental constants. It tells us, for example, that the density of dark energy cannot be 10 times larger or 100 times smaller than what we measure, because such a universe would be unrecognizable. The simulation ensemble acts as a cosmic filter, sifting through infinite possibilities to show us which recipes are viable for producing a cosmos that can eventually ask questions about itself. This is how we move from measuring the universe to understanding its underlying blueprint. The simulations reveal that our existence hinges on a delicate balance, a specific and narrow slice of parameter space that allows for billions of years of structured growth, the formation of stars and planets, and the emergence of complexity. By exploring the multiverse of what could have been, we gain a much deeper appreciation for the precise and seemingly fine-tuned universe we call home. This fine-tuning of cosmic parameters reveals a universe built on a delicate balance, but it also generates an ocean of data so vast it threatens to drown discovery. A single state-of-the-art simulation can produce petabytes of information. the digital equivalent of millions of high-definition movies. Within that staggering volume lies the subtle signature of every dark matter clump, every galactic merger, every streaming filament of the cosmic web. No human, or even a team of humans, could ever hope to sift through it all by eye to find the most unusual structures or the faintest correlations. To navigate this new frontier, cosmologists are turning to a revolutionary partner: artificial intelligence. This is not about replacing human intuition, but about augmenting it with a new kind of perception. Scientists are now training machine learning algorithms on these simulated universes, teaching them to see what we cannot. The process begins by feeding the AI thousands of labeled examples from the simulation. For instance, researchers might show it millions of simulated galaxy clusters, each tagged with its precise properties, mass, shape, age, and merger history. The algorithm, often a deep neural network, learns to recognize the complex, multi-dimensional patterns that define these objects. Once trained, this digital scout can be unleashed on entirely new simulation data, or even on real observational data from telescopes, to perform tasks at incredible speed and scale. It can scan a virtual sky the size of the observable universe and instantly flag the 100 most unusual galaxy clusters, the ones with bizarre shapes or strange satellite arrangements that might indicate a recent catastrophic collision. It can classify millions of galaxies by their type: spiral, elliptical, or irregular, with a consistency no human team could match. But the true power of this partnership goes beyond simple categorization. Machine learning excels at finding hidden connections. It can analyze the simulated properties of 100 million virtual galaxies, their masses, spins, star formation rates, chemical compositions, and local environments, and discover subtle, non-linear correlations that no scientist ever thought to look for. Perhaps the algorithm reveals that a galaxy's chemical abundance is not just linked to its mass, but to a specific combination of its merger history and the density of the cosmic web filament it resides within. These are relationships buried in dozens of variables, patterns too complex for our linear logic to easily discern. The AI acts as a guide, pointing to these hidden links and saying, "Look here, there is something interesting." It is then up to the human scientist to interpret that connection, to understand the physics that might explain why such a correlation exists. In this way, the simulation provides the perfect training ground, a universe where we know the ground truth for every object. We can train an AI to recognize the signature of a galaxy that is about to have its star formation quenched by a central black hole, and then set it loose on real data to find candidate galaxies in our own universe that are on the cusp of this dramatic transition. We are entering an era where our digital twins of the cosmos are not just for us to watch, but for intelligent systems to explore, mining them for secrets and returning to us with maps to treasures we would have otherwise walked right past. The nature of dark matter remains the greatest unknown in our cosmic recipe. For decades, the leading candidate has been something called cold dark matter. This model assumes the dark matter particle is heavy and slow-moving, emerging from the hot early universe with virtually no intrinsic motion. This coldness allows it to clump together effortlessly under gravity, starting with the tiniest of scales and building upward, perfectly producing the cosmic web and the nested halo structures we see in our most detailed simulations. But what if that assumption is wrong? What if dark matter is not cold but warm? This is not a minor tweak. It is a fundamental shift in particle physics with profound consequences for the shape of the cosmos, and we can explore its implications only by building alternative universes inside our computers. Warm dark matter proposes a lighter, faster-moving particle. In the early universe, these particles would have had a significant amount of thermal motion, a slight buzz of kinetic energy. This subtle warmth has a dramatic effect on cosmic architecture. That intrinsic motion acts like a cosmic smoothing iron. it washes out the very smallest density fluctuations, preventing dark matter from clumping together on the tiniest scales. In a warm dark matter universe, there is a minimum size for a dark matter halo. Nothing smaller can form. To test this idea, scientists run a new suite of simulations. They start with the same cosmic seed and the same laws of gravity, but they change one fundamental rule, replacing the cold, sluggish dark matter particles with warmer, more energetic ones. Then they press play and watch an entirely different cosmic history unfold. The difference is striking. In the cold dark matter simulation, as we have seen, the cosmic web is intricate and fluffy with countless tiny halos, like a dense forest with undergrowth at every scale. The warm dark matter simulation reveals a cleaner, more streamlined cosmos. The largest filaments and massive clusters still form. The grand architecture of the web remains. But the fine details are missing. The smallest filaments are smoother. The forest has been thinned. Most dramatically, the countless tiny dark matter halos that should swarm around a galaxy like the Milky Way simply do not exist. They were erased before they could ever form, smoothed away by that primordial particle motion. This single change in the simulation's initial conditions addresses the persistent puzzles head-on. The missing satellites problem. In a warm dark matter universe, those small halos were never there to begin with, so there are no failed galaxies to account for. The too big to fail problem. The warm dark matter scenario naturally suppresses the formation of the very densest, most massive subhalos. The few satellite halos that do manage to form are less dense and less massive, aligning much better with the faint, puffy dwarf galaxies we actually observe orbiting our galaxy. The simulation provides a clear, testable prediction. If dark matter is warm, we should see a stark cutoff in the number of small galaxies, a quiet galactic neighborhood without a swarm of ultra-faint dwarfs. This creates a thrilling observational challenge. Astronomers are now engaged in a cosmic census, using the most sensitive telescopes to scour the halos of the Milky Way and Andromeda, searching for the faintest possible dwarf galaxies. The simulations give them a target. The cold dark matter model predicts a rich population of hundreds of these faint clumps of stars. The warm dark matter model predicts far fewer. Every new discovery of an ultra-faint dwarf galaxy is a data point in this grand experiment. So far, the observations are subtle and the debate is active. We have found more faint satellites than the simplest warm dark matter models predicted, but still far fewer than the pure cold dark matter simulations produced. This suggests the truth may lie in a middle ground, or that other physics, like the fierce feedback from the first stars, is also playing a major role in suppressing small galaxies. The crucial point is that without these competing digital universes, we would have no framework to interpret what we see. The simulations transform an abstract particle physics debate into a concrete, observational test. They allow us to ask the universe a direct question. Does the pattern of lights in our local sky match the prediction of a cold cosmos or a warm one? By comparing the real distribution of galaxies to these simulated alternatives, we are not just mapping the cosmos, we are conducting a fundamental experiment on the nature of reality itself, using the universe as our laboratory. The most astonishing pattern revealed by these simulations is not a shape in space, but a direct line of cause and effect stretching across nearly 14 billion years. It connects the very smallest things we can describe, quantum fluctuations, to the largest structures we can see, the great clusters of galaxies. This chain of events begins in the first fleeting moments after the Big Bang, when the universe was a seething, microscopic foam of energy. At this quantum scale, empty space is not truly empty. It is a turbulent sea of virtual particles flickering in and out of existence, creating tiny, random variations in density. These are the quantum fluctuations, the faintest possible ripples in the fabric of reality itself. As the universe expanded and cooled at an unimaginable rate, these quantum ripples were stretched, frozen into the fabric of space, becoming the classical density variations that would shape everything to come. They are the primordial seeds of all structure. For hundreds of thousands of years, these seeds lay dormant within the hot, opaque plasma of the early cosmos. Then, when the universe cooled enough for atoms to form and light to travel freely, those frozen ripples were imprinted onto the sky. This is the cosmic microwave background, that ancient afterglow map. Its pattern of slightly hotter and slightly colder spots is not random noise. It is the direct, one-to-one imprint of those initial density ripples. A slightly denser region in that early plasma appears as a slightly warmer spot in the microwave background. A slightly emptier region appears as a slightly cooler spot. This map is our ultimate starting point, the universe's own baby picture, and it holds within its subtle texture the entire blueprint for the cosmic web. This is where the simulation performs its most profound magic. It takes that precise map, the exact pattern of hot and cold spots measured by satellites like Planck, and uses it as the initial condition. The simulation does not guess at the starting point, it uses the real one. Then, it applies the unyielding force of gravity and lets time run forward. We watch as gravity begins its patient work. Those slightly denser regions, the warm spots on the ancient map, have a tiny bit more mass. That extra mass exerts a slightly stronger gravitational pull. Over millions of years, this pull attracts more dark matter and gas from the surrounding areas. The overdense region grows, becoming a gravitational well. Meanwhile, the slightly emptier regions, the cold spots, have less mass. They exert a weaker pull, and matter slowly drains away from them toward the neighboring denser areas. As the simulation advances, we witness the amplification of these tiny differences. A minuscule 1 part in 100,000 variation in density in the early universe becomes, over billions of years, a vast galaxy cluster containing the mass of 1,000 Milky Ways. The original cold spot, now drained of matter, has become an immense cosmic void spanning hundreds of millions of light years. The simulation traces this evolution with perfect fidelity. We can literally tag a specific, tiny warm spot in the simulated cosmic microwave background and follow it forward in time. We watch as it gathers a halo of dark matter. We see gas flow into that halo and ignite into the first stars. We observe that small proto-galaxy merge with others, growing through collisions, until it becomes a giant elliptical galaxy at the heart of a massive cluster. At the same time, we can follow a specific cold spot. We see it gradually empty out as matter streams toward the growing filaments around it, until it becomes a profound emptiness, a bubble in the cosmic foam. This causal chain is the ultimate revelation. It means the distribution of galaxies on the sky today is not accidental. The Great Wall of Galaxies in the constellation Coma, the vast Boötes Void, the local group of galaxies that includes our Milky Way and Andromeda, all of these are the grown-up children of specific ripples in the infant cosmos. The simulation shows us that if we could take a map of the cosmic microwave background and a map of all the galaxies in the universe, and then mathematically stretch and evolve the first map according to the laws of gravity, we would arrive at the second. They are the same pattern seen at the beginning and the end of the story. This connection solves a deep philosophical puzzle about our place in the cosmos. We are not living in a special or privileged location. We are the product of a specific, random quantum fluctuation that happened nearly 14 billion years ago, one that grew under the universal laws of physics into the rich galactic environment we call home. Our local universe, with all its splendor and emptiness, is the inevitable outcome of a specific set of initial conditions playing out under gravity's relentless hand. The simulation allows us to trace our own cosmic ancestry, linking the quantum fog of creation directly to the island of stars we orbit today. Yet for all their breathtaking power, these digital universes are not reality. They are intricate approximations, masterful paintings of the cosmos that are inevitably constrained by the brush and canvas we use to create them. Every simulation, no matter how sophisticated, is built upon a foundation of assumptions and compromises. The first and most fundamental limit is resolution. We cannot simulate every atom, every star, or even every small dark matter clump in a galaxy the size of the Milky Way. The computational cost would be unimaginable. Instead, we use those superparticles and grid cells, each one representing a vast collection of real-world material. This means a simulated galaxy is not a smooth, continuous entity, but a collection of discrete chunks. The behavior of these chunks is governed by the laws of physics we program in, but they can only interact on scales larger than their own size. Imagine trying to model the flow of water through a city's pipes using only buckets. You can get the general direction and volume correct, but you will miss all the fine details of turbulence, the tiny eddies, and the precise pressure at every joint. In a cosmological simulation, this finite resolution means we cannot directly see the formation of individual stars or planets. Their birth happens on scales far smaller than our smallest grid cell or lightest superparticle. To account for this, scientists must use recipes, simplified models for processes they cannot directly simulate. This is known as sub-grid physics. For example, we know cold, dense gas clouds collapse to form stars. But we cannot watch a single gas cloud in our simulation do that. Instead, we create a rule, an algorithm that says, when a cell of gas in our simulation becomes sufficiently dense and cold, we will convert a certain percentage of its mass into a virtual star particle, based on our understanding of star formation in the real universe. We have similar sub-grid recipes for supernova explosions, black hole feedback, and the spread of heavy elements. These recipes are informed by theory and by smaller scale, more detailed simulations, but they are still simplified stand-ins for unimaginably complex reality. The danger is that the outcome of the entire simulation can become sensitive to the precise details of these recipes. Change the efficiency of star formation in your subgrid model by a small amount, and you might end up with a universe that is too bright or too dim. This forces scientists to constantly calibrate their models, tuning these subgrid recipes until the large-scale output of the simulation, like the cosmic web or the number of galaxies, matches what we actually observe. It is a careful, iterative dance between theory and observation. Another hidden challenge is the potential for numerical artifacts. These are structures or behaviors that arise not from the physics, but from the computational method itself. The geometric shape of the simulation's grid can sometimes imprint a preferred direction on the results. The way gravity is calculated for distant groups of particles can create faint, ring-like distortions in the distribution of matter. Even the random numbers used to generate the initial cosmic seed can leave a subtle statistical fingerprint on the final virtual universe. Distinguishing a true cosmic signal from a numerical artifact is a critical and ongoing part of the work. The most important lesson is this: a simulation is not a replica. It is a tool for understanding. Its true power is not in creating a perfect digital twin, but in generating controlled experiments. We can run two simulations that are identical in every way except for one single parameter, like the strength of dark energy or the nature of the dark matter particle. By comparing the two outcomes, we can isolate the effect of that one change on the growth of cosmic structure. We can ask, if dark matter is warm, how does the pattern of galaxies differ from the cold dark matter prediction? The simulation gives us a clear side-by-side comparison. Then we take that predicted difference and look for it in the real sky. The simulation's value is proven when its forecasts guide our telescopes to new discoveries, or when its stark predictions create tensions that force us to rethink our fundamental assumptions. It is in the fertile gap between the digital universe and the observed one that the deepest progress is made. Each mismatch is not a failure of the code, but a signpost pointing toward physics we have not yet understood, a hidden layer of reality waiting to be added to the model. The simulation is the ultimate question-asking machine, and the real cosmos holds all the answers. The true power of this digital laboratory is measured in moments of perfect alignment. After decades of development, there have been several instances where the simulation's predictions were so precise, and their later observational confirmation so clear that they transformed our entire understanding of cosmic history. One of the most profound of these convergences involves not the bright galaxies themselves, but the darkness between them. For years, astronomers studying the most distant objects in the universe, quasars, noticed a strange pattern in their light. A quasar is the brilliant core of a young galaxy, powered by a voracious supermassive black hole, and its light travels across billions of light years to reach us. When scientists broke this light into a spectrum, they did not see a clean, continuous rainbow. They saw a forest. It was a thicket of hundreds of dark absorption lines, all clustered in a specific part of the spectrum, known as the Lyman-Alpha forest. Each of these lines is a fingerprint. It is created when the quasar's light passes through a cloud of neutral hydrogen gas floating in the vast intergalactic medium. The gas absorbs a very specific wavelength of light, leaving a tiny, dark bar in the quasar's spectrum. A single line means the light passed through one cloud. Hundreds of lines mean it passed through hundreds of clouds along its immense journey. For a long time, this forest was a beautiful but confusing mystery. What were all these clouds? Were they isolated blobs? Were they the remnants of shattered galaxies? The simulations provided a stunning and elegant answer. When researchers modeled the evolution of the cosmic web, they paid special attention to the fate of ordinary matter, the hydrogen gas that did not end up inside galaxies. The simulation showed that this gas did not simply vanish. Instead, it was woven into the very fabric of the cosmic web itself. After the Epoch of Reionization, most of the hydrogen in the universe was ionized, but not all of it. Significant amounts of neutral hydrogen were left, clinging to the dark matter filaments like a fine, cosmic mist. This mist was not smooth. The gravitational pull of the Webb's structure caused the gas to collect into an intricate, frothy network of sheets, filaments, and faint clouds. This was the intergalactic medium, and it was far more structured than anyone had imagined. The simulation made a specific, quantitative prediction. If you took the simulated distribution of this gaseous web at a certain point in cosmic history, and you simulated a beam of light traveling through it from a distant quasar, what would the spectrum look like? The answer was a synthetic Lyman-Alpha forest. The virtual absorption lines created by the simulated gas clouds matched the statistical properties of the real forest with astonishing accuracy. The spacing of the lines, their depths, their clustering patterns, all of it emerged naturally from the model of the cosmic web. This was a revelation. The Lyman-Alpha forest was not a collection of random clouds. It was a shadow graph, an X-ray of the universe's large-scale structure. Each absorption line was a probe, a measurement of a single filament or knot in the gaseous cosmic web at a specific distance. By studying thousands of quasar spectra, astronomers could now map the three-dimensional distribution of this faint intergalactic gas, tracing the very same filaments that the dark matter simulations had first predicted. The convergence was perfect. The simulation had predicted a detailed, quantitative property of the universe. the statistical signature of the intergalactic medium, and observation confirmed it in exquisite detail. This alignment did more than solve a puzzle, it validated the entire simulation enterprise. It proved that our models of gravity, dark matter, and cosmic evolution were not just abstract mathematics, they were an accurate description of reality on the largest scales. The invisible architecture of the cosmos, first glimpsed in the glow of a supercomputer, was now being traced in the ancient light of quasars, confirming that we are, at last, reading the true blueprint of the universe. The forest of absorption lines proved the cosmic web is real, but it also revealed the limits of our current maps. To see the finer threads of this web, to watch individual galaxies being born from the gas within them, we need a new kind of computational lens. The next leap is already underway, moving from petascale to exascale computing. An exascale machine is a system capable of performing 1 quintillion calculations per second. That is a 1 followed by 18 zeros. This is not merely an incremental step, it is a fundamental shift in what is possible. With this staggering power, simulations can achieve 2 revolutionary goals simultaneously: immense volume and exquisite detail. Imagine a virtual universe that is not just a representative cube, but a volume so vast it encompasses a significant fraction of the observable cosmos, while its resolution is so fine that it can track the collapse of a single giant molecular cloud into a cluster of stars. For the first time, we will be able to simulate a huge, statistically representative slice of the universe, while also directly modeling the formation of individual galaxies from the ground up, without relying on simplified recipes for star formation. The supernova feedback that regulates galaxies will no longer be a sub-grid estimate. It will be the direct consequence of tracking the life and death of millions of individual star particles. This will allow us to witness the delicate interplay between the large-scale cosmic currents and the small-scale astrophysical fireworks that ultimately determine a galaxy's fate. The blurry pixels of our current cosmic pictures are about to become a sharp, high-definition film. The ultimate expression of this power is a project that sounds like science fiction, the creation of a full digital twin of our own Milky Way galaxy. This is not a statistical model or a generic spiral. It is an ambition to simulate a galaxy that, when its virtual clock reaches the present day, looks exactly like the one we live in. The simulation would start from the same primordial seeds that gave rise to our local cosmic neighborhood. It would incorporate the known merger history, including the cataclysmic collision with the Gaia sausage galaxy that shaped our galactic core billions of years ago. It would track the orbits of hundreds of billions of star particles, each one representing a single star or a tight cluster, allowing them to move and interact with precise gravitational dynamics over the entire age of the universe. The output of such a simulation would be a perfect dynamic counterpart to the greatest map of our galaxy ever made, the data from the Gaia Space Telescope. Gaia has provided precise positions, motions, brightness, and colors for nearly 2 billion stars in the Milky Way. It is a frozen snapshot of our galactic present. The digital twin would be the full movie. Scientists could then perform the ultimate comparison. They would take the simulated galaxy, fast-forward it to the present virtual day, and generate a synthetic Gaia catalog from its billions of virtual stars. They would then compare this synthetic data to the real Gaia data, star for star, stream for stream, not in a broad statistical sense, but in a detailed forensic matching. Where do the simulations predict stellar streams that we have not yet found? Does the virtual galaxy contain groups of stars with unusual chemical signatures or orbits that point to a forgotten merger, guiding astronomers where to look next in the real data? Any mismatch becomes a clue. If the real galaxy has a feature the simulation cannot reproduce, it points to a gap in our physics, perhaps a missing merger event or an underestimated effect of the central black hole. If the simulation produces a structure we later discover, It validates our entire understanding of galactic archaeology. This digital twin would become a living laboratory for our home. We could rewind to watch the precise series of collisions that built the Milky Way's thick disk and stellar halo. We could fast forward to see the future collision with Andromeda unfold in detail, or test how a passing dwarf galaxy might perturb our solar neighborhood. It transforms our galaxy from a static, complex environment we struggle to decipher into a narrative we can replay and interrogate. The path to this twin is paved by Exascale machines, but it is guided by the increasingly precise data from telescopes like Gaia. We are moving from simulating universes in principle to simulating our universe in practice. The goal is no longer just to understand how galaxies form, but to reconstruct the specific biography of our own cosmic island, written in the motions of its stars and revealed through the mirror of a digital twin. This shift from passive observation to active experimentation marks a philosophical turning point in our relationship with the cosmos. For most of human history, astronomy was a spectator sport. We looked up, we charted the lights, we told stories about them, but we could not intervene. The universe was a grand, untouchable spectacle, its inner workings hidden behind the veil of distance and time. We could form theories, but testing them was extraordinarily difficult, limited to the rare cosmic experiment nature happened to provide, like a supernova or a passing comet. Cosmology, the study of the universe as a whole, seemed destined to remain a historical science, forever piecing together clues from a single, unrepeatable past. Simulations have shattered that limitation. By building digital universes from first principles, we have constructed the ultimate cosmic laboratory. We are no longer just archaeologists sifting through ruins. We are now architects who can run blueprints, test materials, and see which designs hold up. This transforms cosmology into a true experimental science. We can pose a what-if question, change a single parameter in the code, and witness the consequences play out over billions of virtual years. We can run the experiment 1,000 times with 1,000 different random seeds to understand the role of chance. This experimental power does more than just test ideas. It reveals a profound truth about the nature of reality itself. The breathtaking complexity of the cosmos, the swirling galaxies, the vast voids, the intricate web, all of it emerges not from magic or arbitrary whims, but from the relentless, deterministic application of simple physical laws. Gravity, the nuclear forces, the rules of thermodynamics, these are the only ingredients. When we feed them into the simulation, along with that ancient map of quantum ripples, the universe we know faithfully reconstructs itself. There is no need for additional guiding hands or hidden plans. The pattern is inherent in the recipe. This suggests something astonishing about our universe. It is, in principle, knowable. The chaos is not fundamental, it is emergent. The apparent randomness of the night sky, the specific location of each star, is the outcome of a deterministic chain of cause and effect that began at the dawn of time. Our ability to capture that chain inside a machine, to predict the large-scale structure of everything from the faintest wisp of a dwarf galaxy to the grand sweep of the cosmic web, points to a cosmos built on a foundation of comprehensible logic. It means the universe is not just a collection of objects, but a process, a computation unfolding according to a set of rules we are slowly deciphering. This computational view does not diminish the wonder, it deepens it. The fact that the human mind, using mathematics and silicon, can mirror the creative logic of the cosmos is a profound connection. We are not separate from the universe, we are a product of its laws, and now we are using those same laws to understand our own origins. The simulation is more than a tool, it is a mirror, reflecting back the elegant, lawful, and ultimately comprehensible nature of the reality we call home. These digital universes are more than just sophisticated animations. They are the essential instruments of modern cosmology, a new kind of sense organ that allows us to perceive the hidden architecture of reality. Where our telescopes see only scattered points of light, the simulation reveals the grand narrative, the connective tissue woven from dark matter and sculpted by gravity over billions of years. It lets us see in space what our instruments cannot, tracing the invisible filaments of the cosmic web. It lets us see in time, rewinding and fast-forwarding through the life cycles of galaxies. And it lets us see in substance, mapping the dark components that command the cosmos from the shadows. This is not a replacement for observation, but its vital partner. The simulation makes predictions that guide our telescopes, and the telescope's data, in turn, refines the simulation's code. It is a continuous dialogue between the possible and the actual, a feedback loop of discovery that is steadily refining our story of everything. This entire endeavor stands as a pinnacle of human curiosity and intellect. We have taken the fundamental laws of physics, written in the language of mathematics, and translated them into a dynamic, visual story of cosmic evolution. We are no longer just stargazers, we are universe builders. We have constructed a mirror for reality inside our machines, and in its reflection, we see not only the cosmos but also the remarkable power of our own minds to comprehend it. As computing power grows toward the exascale and our observations become ever more precise, these digital twins will only deepen in fidelity. They will guide us to the next layer of cosmic mysteries, perhaps revealing the true nature of dark matter, the detailed fate of our local galactic group, or the ultimate destiny of the universe itself. The simulation is our vessel for sailing into that future, a tool that turns the vast, silent cosmos into a story we can finally begin to read.